Welcome to DCL 093 Part 2 and to the allergy season in Texas. You will note that I'm going to mute the mic once in a while and I'm probably going to have problems pronouncing some words. I am fighting allergies again, and if I wait for the allergies to go by, I'll never get these videos done. So please bear with me and excuse some of the follow-ups and hesitations you're about to hear. This time around, I want to talk about the dBm, which is a derivation of the dB. And really, if you're going into two-way radio or land mobile radio as a technician or even as a salesperson, the dBm is important to you. If you're into ham radio, I'm here to convince you that learning about the dBm will benefit you as well. I will also do a quick talk about calculating wavelengths, although I really get into that much more heavily in the 400 series. Okay, so dB versus dBm, what are we really talking about? Well, remember the dB was a way to represent very large or very small ratios using simple numbers. For our context, we're talking about power ratios, although it could be current or voltage or audio levels, but we're just going to stick with power ratios. The dBm does everything the dB does, but it gives us the cool option of specifying a quantity, whether it's very large or very small, with simple numbers as well. Let's say we agree that we're always going to make P1 or P2 the same number, like a reference power level. If we did that, we could take a wattmeter reading and compare our reading to the reference and express our reading as a number of dB above or below the reference level. There are times when this is really convenient. Problem is, what reference level? Now take a look at the formula for dBm. Well, this isn't the complete formula because, like I said, when you apply it, either P1 or P2 will be the reference level. The thing is, what are we going to use for a reference level? Well, notice the little m. The decision has already been made for us. The reference level will be 1 milliwatt, or 1 millivolt, or 1 milliamp, whatever you're comparing. But in our little world, we're concerned with power levels. So 0 dBm is 1 milliwatt. That is to say, 1 milliwatt is 0 dBs away from itself. So 0 dBm is not no power, it's 1 milliwatt. All right, fine. So what's 100 watts in dBm? Well, actually, there's no need to do any math here. We already know that 1 milliwatt is 0 dBm. If I increase my power 10 times, I gain 10 dB. If I increase my power 10 more times, I gain another 10 dB. If I increase it another 10 times, I get another, and on we go. So we would say 100 watts is 50 dBm because it's 50 dB above a milliwatt. All right? If 100 watts is 50 dBm, how much is 200 watts? Again, there's no reason to do any math. We already know that if you were to take 100 watts and double it, you'd be adding 3 dB. So that means 200 watts has to be 53 dBm. We can check that. Let's do the math. Take the log, multiply times 10. 200 watts is 53 dBm, and we've done no math. Well, we've done math to check ourselves, but we really didn't need to do any math. The secret is know what 10 dB is and what 3 dB is. You can do a lot. All right, so what's 150 watts in dBm? It's halfway between 50 and 53 dBm, so it must be 51.5 dBm, right? Well, no, it can't be, because the dB scale is logarithmic. So let's find out what it really is. Let's do the math. Take the log. 51.76 dBm. We probably would just say 52 dB. But the point is, notice that it's not 51.5, although you should also notice that the estimate of 51.5 was not off by very much. As a matter of fact, if we were to say 52 dBm, what would 52 dBm actually be? Well, let's take a look here. 52 dBm, let's see. If I had 100 watts and I added 2 dB, that would be 100 watts times 1.58. So this would be 158 watts if it really was 52 dBm. So now you understand dBm, but you might be asking, does this really get me anywhere? Actually, it does. There's a good reason to learn this. You already know that transmit power is measured in watts. How could we evaluate received energy levels and compare them to transmit levels? Now, I know you're probably thinking, oh, what did you just say? Well, if you transmit with 100 watts to me, and I receive you on my 2-meter radio very, very weak, like at 1/4 of a microvolt, you'll be noisy, but I'll be able to hear you. The question is, how many watts are you putting into my receiver at that level? And admittedly, it's almost the minimum signal I can hear you at. Well, you might think, how do you calculate that? You take the voltage and square it, and you divide it by the resistance. What's the resistance? Well, it's the impedance of your radio. My 2-meter radio at the antenna connector on receive is approximately 50 ohms. So all I need to do is put the numbers in there and do the math, and I find out that's a picowatt. So I have a fraction of a picowatt out of your 100 watts. That's how much power you're putting into the front end of my receiver. Now, how would I describe that as a ratio? Well, 100 divided by that number is a very, very big number, and it's almost hard to grasp. But if we take this formula, and remember, we've got 2 levels now. I want to know how far this is from your signal. Well, let's compare it to a dBm first. So a dBm, that is 0 dBm, would be 0.001. And I want to put my level on the bottom because remember, we always put the biggest number on top. So that's what I do. Then I do the division. Then I take the log and I multiply times 10. But remember what this number is. It is telling me that my received signal is 119 dB below 0 dBm. So I would say I'm hearing you at a minus 119 dBm. You're transmitting, what did I say? 50 dBm. What's the difference in your power level versus the power you're delivering to my receiver? Now let's take a look at this. So I'm hearing you at a 1/4 microvolt, which is a minus 119 dBm, but you're sending me 50 dBm. The difference is the difference between plus 50 and minus 119. So 50 minus a minus 119 is 169 dB loss. That is much easier to represent than to say I went from 100 watts to 0.00125 picowatts. By the way, in my corporate training, this is something I teach all the new people, and it's very obvious to you now, as if it wasn't before. Radio is very efficient at transferring information, but it's not very good at transferring power. Notice that at such tremendously small power and such tremendously high loss, I understood every word you said. Now, why would anyone care about how much power appears at the receiver? Well, most of the time, you and I don't care. We just want to be able to hear each other. But there are times when the power level at the receiver becomes really important. Like the level of undesired signals. Any strong signal hitting my receiver, even if it's not on the same frequency, might cause my receiver to not be able to hear you. I'm going to want to calculate the level of interference of nearby transmitters. Or what about this? I put a repeater up on the mountain. I put a duplexer on it so I can use one antenna. So I'm using the same antenna for transmit and receive. My duplexer has to block the transmitted signal from the repeater's receiver. But it doesn't actually do that. All it does is attenuate it a certain amount. So the question is it attenuating it enough so my receiver can hear those weak signals? Well, this is why we do calculations to figure out how much energy is hitting the receiver when the transmitter's on. And I will go into that in a later video. Look in my folder, my YouTube channel folder, for the DCL 700 series. Those videos should appear by May 1st of 2025. Let's wrap up with a quick talk about calculating wavelength. And again, the DCL 400 series deals with this in much deeper detail, but I'd like to do it one more time because this is a video about basic math for radio. Here we have an antenna. It's probably a half-wave dipole, but whatever, it's an antenna. I can't draw for you very easily, or maybe at all, an accurate depiction of the electric wave and the magnetic wave as it leaves this antenna. What I can give you is sort of a graph of that field's intensity. So the field doesn't look like this. This is a graph of the field's intensity as the field leaves the antenna. Now you'll notice right away, it started out and it built in a certain polarity to a peak, then it went to zero, then it built in another polarity, and then back to zero. As you've guessed by now, that's one cycle, or 1 hertz. But it's also, if you could measure the distance in the air from here to here, that would be your wavelength. So this whole thing is about how far it is from the beginning of a wave to the ending of that wave, which is of course also the beginning of the next wave. Well, talk about a string of waves. Let's do this. Let's turn the transmitter on for 1 second. At the end of 1 second, we're going to do 2 things. First of all, we're going to turn the transmitter off, but second of all, we're going to freeze time. We now have these electromagnetic waves hanging in space, standing still. Of course, that's impossible, but we're kind of playing God here for a minute. At the end of 1 second, the leading edge of the wavefront will be 300 million meters from the antenna, because these waves move at 300 million meters per second. All right? Is there a way to determine in feet, inches, meters, whatever, how far it is from here to here? That is, of course, a magnification of the distance from here to here. I just wanted to be clear. Can we do that? Well, actually we can, because we know that all these waves are evenly spread out over 300 million meters, because we're only talking about what happens inside of 1 second. So if we were to divide 300 million meters by the number of hertz, or number of cycles in the RF energy, we would know how much distance each one takes up. Let's pick on 150 million hertz, which is, of course, 150 megahertz. Well, now we know 300 million divided by 150 million, that's 2. So that means it's a distance of 2 meters from here to there. And that repeats throughout the whole wave, the whole distance. Now, those of you who remember a little bit of math will realize that this is a ridiculous way to calculate this, because everything we do in radio, well, most of the time, is in megahertz. And we learned in school that you can cancel duplicate zeros. I call them duplicate zeros. That's not a very good mathematical term, but you know what I mean. That's where this comes from. That's how we ended up with 300 divided by f in megahertz for a wavelength. All right, so let's have some fun here. Let's say you are on exactly 10 megahertz. You do the division. Oh, that's right. That's the 30-meter ham band. All right, so if the wavelength is 30 meters, that means a half wave is 15 meters and a quarter wave is 7.5 meters. Now I know how long to cut my antennas, don't I? Well, no, you don't. Because RF currents flow slower in antenna wires and tubing than they do as an electromagnetic wave in the air. So what you'll do is you'll multiply the above by either 3.28 for feet or 3937 for inches, or you won't multiply it by anything because you've got a metric tape measure. But the last thing you're going to do is you're going to multiply the above by the correction factor to get the electric length, not the length in free space. Before I give you that, it's convenient to answer the question, where does 468 divided by f come from? This is supposed to magically give you a half wave antenna length in feet. Well, this topic and the correction factor kind of work together. We want a half wave dipole. So instead of 300 divided by f, we say 150 divided by f. Oh, excuse me. But we want this in feet. So what we do is we multiply 150 by 3.28 to give us feet. Now we're getting close to 468. The next step is we put in the correction factor. 4.9% speed reduction from free space to wire or tubing. That makes it 0.951. That's where we get 468. Now, about that number is a bit of a problem. You've probably, maybe, you've used 468 divided by f, and it's worked perfectly. Other times, you find yourself trimming wire or adding wire. That's because pretty much what this correction factor does is it takes into account the slower propagation of RF current in the wire as opposed to the EM wave in free space. But there's some other things that happen with antennas. You may have heard of end effect, and that is objects off the end of the antenna will mess around with the field. That messing around with the field feeds back into the current and throws things off. So if you've got objects close to the antenna or the antenna is closer to the ground than the designer intended, this number has to be adjusted. So 0.951 is a really good starting point, and 468 divided by f is a starting point, but it doesn't work all the time. One more thing. I didn't mention this before, but you can calculate the wavelength in a piece of coax. So you do all the same math. But with coax, it's much easier, because with coax, there's only one thing affecting you, and that is the velocity factor of the cable. The manufacturer will do a test and determine how much slower the currents flow in the coax than the electromagnetic waves will flow in free space. And they will issue a velocity factor. The coax I just bought has a velocity factor of 0.89 or 89%. So if I multiply times 0.89 and cut my cable, I will have my quarter wave or half wave or whatever length of cable. Now, the reason you would cut cable into certain lengths like that is if you're making a matching harness or you're phasing antennas or something like that. The point is, with coax, it's very easy. You just look up the velocity factor in the spec sheet for the cable. Or, and I'll show you this in a later video, you can use your VNA or other test equipment and you can actually measure velocity factor of coax very accurately with amateur test equipment. Look for that in one of my other videos as well. Thank you so much for watching. I hope this wasn't too much to take on in 20 minutes. I feel like I went through it way too fast. But the point is, if you can grasp the concept of the dBm, I wouldn't worry too much about the wavelength calculations. I go into that a lot heavier in the 400 series. Thanks so much for watching. I hope this was well worth your time. By the way, I never say this. Please put positive or negative comments in the comment section of my videos if you can, because it's easy to teach this at the corporate level when I have 10 faces looking at me. This YouTube stuff is very hard because I'm not getting any feedback. Therefore, I don't know if I'm doing a good job or not. Thanks again. See you next time.